Welcome to the Abaqus tutorials, Response Spectrum Analysis. Response spectrum analysis, what is it? So spacecraft and launch vehicle components can encounter mechanical shock from a variety of sources. And these tend to be short transients that could have high amplitude. The shock loading is a rapid input of energy to a system. Here you see a plot of the G loading versus time, and you can see here that it's a very short time duration, and it does put quite a bit of transient high energy event into the system. And it can contain frequencies up to 10 kilohertz. The shocks may not travel very far from the source. Sources of shock inputs can cause damage to electronics, and it can involve rocket motor ignition, staging, fairing SEP, deployment events, pyrotechnic devices, or a truck riding over a bump that may have been a dramatic bump of some kind. Response spectral analysis estimates the structural response to short, non-deterministic transient dynamic events. Since the exact time history of the load is not known, it is difficult to perform a time-dependent analysis. Due to the short duration of the event, a random response approach may not be the best approach here. The response spectrum analysis can be used to estimate the peak response of a structure due to a particular base motion or force. The method is inexpensive. It tends to be conservative for preliminary designs. It uses a subset of the modes of the system, and then you will then drive the motion of the base to then determine the response of the system. The response spectrum analysis is going to use a linear superposition of the modes and then calculate the total response of the system. So what is response spectrum analysis? What we're looking at here is a time domain input here at the bottom. It's a base acceleration of some kind. It could be a truck going over several bumps. It could be some sort of short duration event, such as any of these here. But you're gonna have a base acceleration. And here you can see that it's a short duration event that goes from 0 to 0.1 seconds. And so what we really wanna do is to come up with a conservative approach that can be used to analyze this problem. Now, you could solve this in a time domain, but notice how many oscillations I have within 0.1 seconds. That's going to, if I want to analyze a huge structure, then I'm going to have to consider a very small time step. And I may have to solve millions of degrees of freedom, and that's going to be very computationally expensive. Another approach that is based on the SRS, and it was developed for earthquake analysis in the 1930s. The way it works is that you consider several or many single degree of freedom systems, and you can see them all here. Every single degree of freedom has been tuned carefully to give a particular frequency. So here you have a single degree of freedom oscillator with a mass, damping, and stiffness of 30 hertz. I could have a single degree of freedom system at 1 hertz, 2 hertz, 3 hertz, all the way, in this example, I have 1300 hertz. And so in this example, what we're going to do is to take this base acceleration, apply it to the rigid base, and all the single degree of freedom systems are subjected to the same base acceleration. But each of these single degrees of freedom systems have different natural frequency. And so the idea here is to determine the response of this base acceleration of the system due to this base acceleration. Here is the response of this mass as it moves, and here is the response of the accelerations over time, over this 0.1 seconds. And you get some sort of amplitude. And then you can examine the 60 hertz oscillator, and you can see here that I get an amplitude. And then I can continue to examine the solution due to this base acceleration for each of the single degree of freedom oscillators, and then you determine a corresponding response of accelerations on this mass for each of the oscillators. And what we're gonna do now is to select the peak response of each of these here, of each of these oscillators. And then what I'm going to do is I'm gonna plot in the y-axis the maximum response for each of these particular oscillators. And so here's a continuous plot, and it was developed by considering many oscillators at various frequencies that varied all the way from 10 hertz all the way to 2000 hertz in this example. But here, on purpose, we've plotted the maximum response at 30 hertz, at 60 hertz, at 200 hertz, at 500 hertz, at 1000 hertz, and 1013 hertz, which corresponds to the maximum response of these masses due to this base acceleration here at the base. And so what I've plotted here is called the SRS response. And this shock response spectra is conservative. And this is what we plan to use to input into the response spectrum analysis. In the tutorial problem that we're going to examine, we're going to be looking at a steel antenna reflector. And here you see the antenna reflector. This tutorial was already developed. The mesh and everything else was developed in a previous tutorial. And I invite you to look at that tutorial carefully. And that tutorial looked at the force response spectrum. So check it out. Try to learn how this mesh was developed and the boundary conditions and all that. In this particular example, we're going to examine a antenna here, and this antenna is subjected to vertical shock that could have been induced by perhaps this antenna was stored on a truck, and the truck was traveling and it encountered a bump. So we're going to look at the pulse due to this event, this pulse event. And so maybe the pulse event was measured to be a half sine pulse, like you see here. Very short duration, as you can see. The G loads went to 40 Gs, and it drops to 0.01. So this is a very high frequency response or input. And so there's a lot of tools that you may find online that can help you come up with the SRS, but in essence, this calculation here that I've done, this acceleration here that I've calculated due to this base acceleration can be determined very straightforward by solving the equations of motion. So it's not a very difficult calculation. So there are calculators online that can help you transform a time input into a SRS response. And so what we're going to do is to apply this SRS response as a base input into the response spectrum analysis. The response spectrum analysis provides an estimate of the peak linear response of a structure due to dynamic motion of the fixed points. In this case, we have that fixed point here at the bottom of this antenna that has been connected with beams to a base, a fixed base. So we're going to assume that the system's response is linear so that it can be analyzed in the frequency domain using its natural modes, which must be extracted in a previous eigenfrequency extraction step. So that's very important to first analyze the structure to determine the modal characteristics of the structure by extracting the frequencies and the mode shifts of the system. And then we're going to use that information to use a response spectrum analysis with the SRS as the input to then determine the total response of the system, okay? And so you're going to use the results, and it's important to understand that the results are conservative. The time and phase information has been lost, of course, because remember the SRS was developed based on a time domain input But remember, the SRS was developed based on the maximum acceleration caused by an oscillator that was tuned at a particular frequency. All stresses and deflections tend to be the worst case predictions, and the deformed shape is not necessarily representative of the actual response. So with that, I'm going to invite a very special guest speaker, Pavel Babuska, who has an expertise in spacecraft launch vehicle analysis and has an expertise in fracture, dynamic, fatigue, and strength analysis. So I invite you, Pavel Babuska, to help us guide us through this tutorial, and I hope you're having a good day. I appreciate your help here.
Hello, welcome back. Thank you for having me again, Vinay. Today we're going to do a different type of analysis. We're doing a response spectrum analysis. So what you have on the screen here is the tutorial problem. This is our steel antenna reflector, same as the random response analysis or the force response analysis that was done last time. Except here, in this case, we're going to be calculating the response of the antenna due to a vertical shock input. So the example case that this would be something like, this antenna is mounted to a spacecraft or it's mounted to whatever, and it's, for instance, being transported on a truck. Truck goes over a bump, shocks the system due to going over that bump, and it transfers that acceleration through the load path and shocks it through the base of this antenna. So the information that you need for this is essentially an estimate of the time domain, input converted to acceleration shock response spectrum. There's tools online that can do this. There's closed form, there's ways of doing this easily, but they're presented here on slide 7 as well. So we're going to leverage the model that was made last time, this reflector model. I'm just going to put that in, change the step type, and then go from there. So go into Abaqus and open this model. Here I have it open. I've done this example. I test ran it. But this assembly looks like this. And so we're just going to use this as a starting point. If we go into the step module, we first need to set up that modal analysis step, same like last time with the random response, force response analysis. So I've rolled back the last version, the analysis that we did, just to have the modal analysis step. So first thing that we need to do here is create the response spectrum step. So let's just call it response spectrum, and it's of this linear perturbation procedure type, and it's response spectrum here. Easy peasy. So first thing that we have, you'll notice there are some drop downs that we need to populate. First, excitations. From the problem statement that we're just going to be shocking it in this single direction. It's not going to be any sort of three-dimensional shock. For simplicity, we're just doing this y-direction shock, so single direction's okay. Summation-wise, we're going to do square root of the sum of squares. So this is kind of like a max on max, like RSS, sort of conservative summation for this type of problem. What it's asking for here in this first direction, or our only direction, is to provide a response spectrum. So Abaqus wants this in a tabulated format. You make this as an amplitude, which is this little button here. So let's go ahead and click that. And let's call this Excel SRS, and it's going to be type spectrum. So it asks you to create this amplitude. Unit-wise, our specification needs to be in gravity units, and we're going to specify that as 9.81 meters per second. And now it's asking for magnitude, frequency, and damping. We're going to have 2% damping through the whole thing. And from that acceleration SRS, we can pluck out magnitude frequency pairs and then input it in a tabulated format. So let's go in here. Here I've basically just copy pasted the acceleration SRS and put little stars on the portions that I want to extract acceleration frequency pairs for. So 2% damping through the whole thing. I'm selecting first one, 1G, 1 hertz, all the way through for these 6 pairs, and I'm truncating it at 1,000 hertz. This is because I remembered that in our, and you'll see later, in the modal analysis step, I just extracted the first 10 modes, and that only goes up to about 850 hertz in the modal content there. So we don't need to run it out to 10,000 hertz because there's no frequency content between 1,000 and 10,000 hertz. So if we copy this stuff here, we go back into Abaqus, you just paste it in here, call it good. Use the response spectrum we just made. Okay, direction cosines. This is basically asking for, what direction is this going to be applied in. We know that we're going to be shocking this all through the y direction, so this is going to be like, none in the x, all in the y, none in the z. With a scale factor of 1, we've already handled, we don't need to scale it. We've got the g's as 9.81. We've got the acceleration SRS in that tabulated form already. Boom, we're good to go. It makes the field output for you, makes the history output for you. We don't need to do anything in terms of new boundary conditions or loads. In fact, there are no loads in this type of step, so you can take off the gravity load that was applied in that force response analysis from before. So no loads, same boundary condition, just that fixity down at the bottom. Nothing to do with the mesh. Everything with that is fine. All we got to do is create a job for it and then run it. So I created a job for this already, and so now I'm just going to submit it. Here we go. All right, we're done. So if we were to check, the modal analysis results, first of all, you might notice that I have the shell thickness and beam profiles rendered here. So if you go into View, ODB Display Options, you can render those. Apply, okay. If we look at displacements, recall this is the same as from our last round of analyses. First frequency is around 22 hertz, 22.5 hertz, and then you get up into these flexible body reflector shell modes, 500 hertz, 600 hertz, 800 hertz, but then nothing beyond that 800 hertz round. So this is exactly why we truncated that acceleration SRS tabulation to 1,000 hertz and didn't take it out to 10,000 hertz. If I would have, requested 20 modes or however many modes that, has modal content out to 5,000 hertz or something, we would want to accommodate that in the tabulation of the acceleration SRS. Okay, so we go into this response spectrum step. One important thing to note here is that the results that are being depicted for this response spectrum step are like non-physical in that they would never occur simultaneously like this for any part of the event. This is an overlay of the field output, so in this case the displacement, an overlay of what the max displacements are for the entire frequency range, essentially. So this type of analysis is used to see what the total displacement state, or like if you were to assemble or overlay all of the results all at once, it would look like this. It doesn't look like this at any particular time point in the time domain, though. Same for stress, same for whatever field output in question. So if we look at this displacement magnitude, this kind of makes sense, right? Because we're shocking it in the y direction. And if you were to sort of roll up all of the displacements that occurred over that whole shock event and plot what it would look like all at once, it would be this like, flared up parts of the reflector at the compliant, portions of where it's being unrestrained. So makes sense. In terms of stress, again, like non-physical representation, but rather an assembly of like, what is the peak stress on all of these things throughout the entire step all at once. And we see here, this is in pascals actually, so 16 megapascals. That's well within the strength of steel. So if I were to look at this, I would say displacement was on the order almost of like microns, and then stress, 10, 20 megapascals. So from a conservative, like first order sense, I would say this design is probably okay, thumbs up. The beams are sized in such a way that you wouldn't expect any like yielding of beams for this type of loading. No problematic stresses in the reflector necessarily. But if you were to have, some stresses that were too high or displacements that were, too high or not correct or whatever, then you would want to, use that information and say, okay, maybe I have to redesign, resize the stuff, or protect for this design in another way. So don't let that, type of shocking happen. You'd want to cushion the thing during transport if you knew that vehicle bumps could produce, acceleration SRSs that looked like that. So this is kind of how you use this information. It's a conservative, kind of non-physical plot of everything that goes on all at once during this entire event. So play around with it. I hope you learned something from this, and thank you again, Vinay, for having me.